Welcome back to separations class. This will be another short Excel tutorial for how to use Excel to plot an XY diagram. Specific example is going to be for the water acetic acid system, assuming ideal behavior at 1.2 atmospheres. And I'll also want to know what value of the relative volatility best represents this data. So this should be a familiar example. This is the exact example system that I used to show you how to plot a PXY and TXY diagram in a previous video. So I'm back on my same Excel sheet, and I'm going to use what we did last time as a starting point. So this is the what we did last time, drawing the TXY diagram, and you're going to find that drawing the YX diagram is pretty simple if you already have all the TXY stuff. So I've got my water and acetic acid Antoine's parameters. Remember that I used Antoine's equation to calculate the vapor pressures for both components. And then my bubble point constraint is given by combining the two Routh's laws using the constraint that the vapor phase mole fractions must sum to 1. So I can do this for either the bubble point or the dew point constraint. I'm just going to pick the bubble point because it's first. So just arbitrarily, I'm going to copy this data over and use that as a starting point to draw my YX diagram. Just going to paste that in here. And what I need to do here is calculate the vapor phase composition that is going to correspond to my X. This is actually another way that you can plot the TXY diagram without having to go through and calculate what this dew constraint is. So I'm going to add a column here, and this is going to be my vapor phase composition of water. And in this column, all I'm going to do is simply solve Routh's law given all the other information. So Routh's law, remember, is Y water times total pressure divided by, equals X water times P star water. So to get what Y water is, I'm just going to divide pressure by both sides. So that's X water times P star water divided by total system pressure, which 1.2 atmospheres converted to millimeters of mercury. We did this last time, 912 millimeters of mercury. And double clicking this down will give me the corresponding Y for the given value of X. So last thing I need to do now is plot this, and I already have my plot ready to go. So this is going to be my YX diagram, and I've already plotted what my YX line looks like. So remember that this line is a good reference line. It's a good habit to put this in there. If you're curious about how to do this in Excel, what I typically do is I've hidden it down here. I just plot the point 0, 0, and 1, 1, and then just plot that. So this line is taking this data, and then you can right-click the line to format it. I just like to outline it in a square dotted dashed line that's just flat black. So I need to input my YX data onto this plot. So I'm going to right-click and click Select Data. I'm going to add my series X values are going to be my X, and my series Y values are going to be my Ys. And there we have it. So this is what the YX diagram is going to look like. I'm just going to make it black so that it stands out a little bit better against the grid lines, and make sure that my aspect ratio is square. So this is what I would expect it to look like. Now the next part of the question asks me to calculate the value of the relative volatility that best represents this data. And in order to do this, I'm going to use Excel Solver to solve for the best fit value of the relative volatility. So I didn't have to solve for Y of water using Routh's law. I can actually solve for Y of water using the relative volatility equation. So this is I'm going to put in a cell my best fit alpha, and I need an initial guess. So I'm going to make the initial guess of 2. Most relative volatilities are somewhere around 2, and I'm going to make a column that says Y, water, and this is going to be based on alpha. So the alpha equation, remember, is X times alpha, and that's going to be $, divided by parentheses 1 plus alpha $-1 times X, and parentheses, and that's looking good. Now these are the Y values that I'd get just by guessing. So I'm going to overlay select data. So I'm going to add X's and Y's. And it's very likely that I made good initial guess. Actually, that's not too bad, right? That's pretty close. The actual answer is going to be close to 2. So I can play with this. I can try different values of alpha. And you should see that as I decrease alpha, this line is going to just pinch in a little bit. So that should make intuitive sense. Remember, alpha is the relative volatility. And the greater my relative volatility is, that means that there's a bigger difference. So these will be easier to separate the greater the value of alpha. So I can try a crazy high alpha, like 8 or 10. You should see that the line bows out a lot. I'm going to put it back to 2 and show you how to use just a simple least squares method to solve for the best fit value of alpha. So I know what the value of y should be, and I know what the value of y given the alpha equation is. So I can set up a column that is going to be the squared error and set that equal to the difference between these. Again, those of you who are in my phase class, we did this a lot this summer, so it's the same method that I'm using. You can use this same method to calculate any parameter that you want. I have to square it because I want to account for positive and negative errors equally. I don't want them to cancel each other out. So these are all the differences between my data points. I'm going to have a cell that adds these all together. So in Excel, the syntax is sum, and that is going to give me a value. Now I'm going to use data solver and use Excel solver to minimize this value by varying what the value of alpha is. So if I choose super high alpha like 10, my error is going to increase. And that reflects the fact that this yellow line is not really matching the black line. So I'm going to put it back at 2, use solver. So set my objective of this cell to a minimum, not necessarily a value of anything, by changing my target cell of alpha and subject to no constraints. I don't have any constraints here. I'm just going to click solve, and that is going to give me an alpha value of 1.82. And if I look at my graph, I've got pretty close agreement now. So I want to point out that water and acetic acid is a system that is not quite likely to be ideal, but if you assume ideal, you can usually assume that the alpha value is going to be constant. So a constant relative volatility here, if you're assuming ideal, is not that far of a stretch. But again, in real life, you're not very likely to have ideal behavior anyway. So that'll wrap up this video. I'll see you in the next video.